Very good. Okay, so I actually wanted to split the class today up into two pieces. The second piece will be sort of more mathematical preliminaries for stuff that we will be doing later on with convex sets and these things like polyhedra. But there were a series of very good questions last time, and I sort of wanted to dedicate a little bit of time to addressing a little bit of the jargon that I've been using and a little bit of what exactly is or is not ruled out by these sorts of no-go theorems that we're going to start covering. So let's see, we go down here. Okay, so if you recall, last time we associated something called a preparation with a density matrix. And then a measurement procedure with something called a POVM. So let's call this a subset. And essentially just, I mean, this is the sort of mixed state generalization of an orthonormal basis. So we're normally used to measurements being like, I have some Hermitian operator, it's got the spectral decomposition, and then when I measure, I get randomly one of these states, which is the same thing as randomly applying one of these projectors. And this is sort of like the mixed state analog. And I will just skip transformations for a second because you can always think of the transformation as updating the state or backpropagating the measurements. So we'll just stick to these. And then we had the Born rule, which was I get some probability k given some measurement, and this was the trace of rho ek. And it occurred to me that last time maybe you guys are not sure why I used the trace here, because I was thinking to actually maybe put this on the homework for people who have not seen like Nielsen and Chuang. Maybe what you've seen before is something more like psi, some operator psi. And this, when rho is equal to like a projector, like ket bra, then these are the same thing. This is slightly more general. Okay, so what I want to sort of talk about is, and I will, so this is why I was talking about the reading materials. I wanted to go through the reference Harrigan and Spekkens. And I should, at the very least, I will let make my handwritten notes available so you guys will have these references to look at. 2010. And so the basic idea is that in an ontological model, so in ontological, we have, so again, we have preparation procedures and measurement procedures. And sort of intuitively, what they have is that a preparation procedure prepares a system in a certain physical state. So actually, I will say this. So in ontic state, lambda is a complete specification of the physical properties of the system. in principle, if you knew this, this is all that you would need to perhaps know about the physical state of the system. So when we discuss preparations within the context of ontological models, and so when we talk about a preparation, there's two pieces to it. There's the actual sort of mathematical representation, and then there's the words that we attach to it. So for a preparation, we usually, what that ends up being in an ontological model is a probability distribution given P. And then this is, so maybe I won't write all of this out, but a preparation procedure prepares a system in a certain epistemic state. So I'll get to the word epistemic in a second. And then what M does is it is going to give us what's called a measurement procedure reveals something about the properties of the system. So M, comma, lambda. So we discussed this briefly last time. So let's go like this, actually. So coming back to the words that I used before, so we're going to say that this, oh, there's a typo here. This here is called the epistemic state. Here this is going to be, so do I have a specific phrasing that I want to use here? State of knowledge of an observer. Of an observer. So this is sort of along the lines of something that you would see in statistical mechanics, where you have many degrees of freedom, and the only reason that you're using probabilities, these Gibbs distributions, is precisely because you can't keep track of all of the different degrees of freedom. So you would say that, you know, the probabilities, I mean, this could be up for debate, but you could argue that the probabilities in statistical mechanics are of this type. They're states of knowledge of an observer, given some constraints. Like the total energy of the system, total, you know, these sorts of macroscopic variables. So in totality, we have that an ontological model is then going to be a set lambda. So an ontological model is a set lambda, and for every P and M, possible preparation and measurement. I think it was you who asked, you know, what determines these preparations and measurements. Essentially, if you're in the lab, you know that I can send my system through a certain set of gates or a different set of gates, and I have some operational restrictions in principle, like I can't maybe in my architecture do any possible gate, and so these P's and M's are specifically determined by whatever sort of experimental setup I have. And so I'm leaving this as being completely general, but in practice, you would know exactly what these P's and M's are because they're restricted by the actual setup that you have. We have the P of lambda given P and P of k given m comma lambda such that trace row or yeah, I mean, if our preparation is rho and we use a particular P of m, then this is going to be an integral over the domain lambda, P of lambda given P of k given m comma lambda. So that's so we wanted to reproduce the Born rules. So this is what an ontological model is, and so what we kind of want to do is to classify these ontological models in a particular way so that we see precisely what is being ruled out, what's the sort of landscape. Keeping in mind that these ontological models are a very specific sort of framework. So in the quantum foundations community, if you're somebody who's like a quantum Bayesianist, which is like a very particular sort of point of view that the quantum state is like just all in your head, and well, if everything is just all in your head, then an ontological model is not going to make sense because this is specifically about properties. There exists some properties lambda out there. Believe it or not, there are people who think that there are views of quantum mechanics where you don't need to posit anything out there. So I will just like leave it as a remark that this does not capture everything. So the no-go theorems inevitably don't no-go everything. There's certain things that are still viable because they don't even fit into this framework. Okay, so, now some more definitions. I had originally planned to sort of steer clear of some of these, it's just like a series of definitions, but I think that it will be important going forward to at least have seen it just once. So, we say that an ontological model is psi complete if one is that lambda is isomorphic to, and I will explain what this is. First, we say that it's psi complete if the state space, the physical, the set of physical states are isomorphic to the projective Hilbert space. What is this object? Basically, if you take your Hilbert space and you take any vector that's not zero, this is a ray in that Hilbert space, and we basically want to say that the projective Hilbert space is going to be the equivalence class of all rays, because we have up to a overall phase. So if the state space is just the set of pure quantum states, and in addition, the preparations are given by a very particular kind of function, this is a psi, equals delta of lambda psi. So what is sort of the reason for this thing? What we're basically saying is that you have an ontological model, you take the wave function itself as your physical objects. So you're taking the set of pure quantum states as your set of physical states, and you're saying that the preparations are this like you're picking out one possible, for any given lambda, the distribution over these lambdas is just a delta function. So as you might expect, so So if OM is equal to, I'll just say, not psi complete, then we say that OM is psi incomplete. Which is just to say that in addition to taking the quantum states themselves as your physical states, you would in addition have some additional states, like maybe the positions of particles or some other microscopic degrees of freedom which specify the physical state of the system. So another definition. So we say that an ontological model is psi-ontic if, and for psi-ontic we have the following. If for any pair of preparations phi and psi for quantum states phi, psi in Hilbert space, we have P of lambda P phi, P of lambda P psi equals to 0. Yeah? This one? Okay, yeah. So an ontological model is a set, not necessarily finite, lambda. So these are your set of physical states. And for every preparation procedure and measurement procedure, we have a corresponding distribution over lambdas given P and a distribution of outcomes given measurement procedure and lambda, such that they reproduce the Born rule. Is this legible? Yeah, okay. So anyone want to take a crack at where this definition is coming from? Maybe I should take a step back. Does this sort of make sense? I mean, just to say that something is psi complete, it's a sort of weird terminology, but the definition, I think, is basically saying that, okay, we have that the states are precisely the quantum states, and any preparation is precisely going to give me a delta function. So basically, this is like the orthodox version of quantum mechanics. I take the quantum state as like the real thing and be over and done with it. Psi-ontic, now, so can anyone sort of make sense of why this would be the condition for something like psi-ontic, just to sort of get our hands dirty a little bit? In particular, if this is a probability distribution over some set, and this is another probability distribution over some set, this condition is saying, what about the distributions? If I had to plot them.
I mean, one of them is always 0 at a given point. So like they don't...
But they can't be 0, right? Because...
No, but they don't over...
Yeah, that's the one. Say it?
They don't overlap.
Oh, yeah, and I guess I'm supposed to announce if you guys have a question for purposes of recording. Are you guys okay with me? Okay. Yes, that's exactly right. What was your name again?
My name?
Yeah.
Merton.
Matin? Yeah, so precisely, this is the condition that they don't overlap. So it's going to be the case that if, and maybe that's the next thing that I say, that if an ontological model is psi epistemic, if it's not psi-ontic. So the or just the converse thing is that there exists some lambda in lambda such that p lambda so let me make sure that this is p phi p lambda sorry p psi not equal to 0. Okay, so we say something is psi-ontic if for every, and maybe I should say for every pair actually. For every pair of distinct preparations, we have that the product of the corresponding distributions are 0. That means that these distributions don't overlap at all, which is to say that if I invert this equation using Bayes' rule, so there's a rule, so I can think of p phi given lambda as being proportional to p of lambda given p phi, right? And so what this one is saying is that if I knew that something was lambda, then I would be able to distinguish these completely because I can't have, given that lambda, I cannot have both p phi and p psi if I just flip this around. Conversely, this one is saying just the opposite, that I have, essentially this one is saying that I have some distribution and I have some Gaussians like this, and there exists some lambda, which is in the support place where this is non-zero and this is non-zero, so that if I just had lambda, if somebody said, hey, the actual state is lambda, I would not be able to say definitely just based on that which one this is coming from. So you might say that this lambda is consistent with several different preparations. So there's a classification table and it goes something like this. So I will just abbreviate psi complete, psi incomplete, psi ontic, psi epistemic. Okay, I'm gonna sort of bug you guys a little bit. So let's see. These boxes here can either be full, that means that it's consistent to write something down that looks like this, or they can be empty. Any hunches on which one is definitely full and which one is perhaps empty? So maybe just we start from, if we start from psi complete and we look at the definition, now we're given what the preparation procedure, this distribution looks like. It's a delta. So will I have any overlaps there between distinct preparations? No. So it's completely valid to have something that's psi-ontic and psi-complete. Because psi-complete implies psi-ontic. Yeah?
And with the same reasoning, you couldn't have psi-complete and psi-epistemic together. Right?
Yes, very good. That's exactly, this one is actually the only one that's empty. Very nice. Can you sort of elaborate on your, how you came to the conclusion? Maybe it's obvious, but it's
So
just,
we have delta peaks, and they have to be the same preparation to have an overlap, and that's everything. Wait, that's the reasoning for the first one.
no, but it's essentially the right reasoning, right? Because you're saying like, if I have to, by definition, this one has overlaps that there can't be any overlap, and therefore this by definition can't happen. It can be the case that you can be psi-incomplete and psi-ontic, because what psi-ontic means is just that you satisfy this condition, but you could have in addition some other physical states like the positions of particles or something. If you've heard about this de Broglie-Bohm theory, it will fit into something here. And sometimes, I guess in the paper, they call this psi-supplemented. Okay, for what it's worth. And then psi-epistemic and psi-incomplete. Yeah, I mean, essentially, this is what psi-epistemic, these are the allowed psi-epistemic models. They have to be incomplete. Essentially, they cannot satisfy these. Okay, very good. You guys answered that, and maybe I should just write also that psi I plus psi O is equal to this psi supplemented. Okay, let's do some examples. Yep.
So does there exist epistemic models? Would you say that?
We are usually going to include the word psi-epistemic there. I mean, because in some sense, you could introduce an element of epistemic. Like if I have a random procedure, right? Like, so if I have that my different procedures are pure quantum states, and then I have a thermal sort of, and I have them hooked up to some thermal bath. So this is like a epistemic situation. Like you have different pure quantum states, and they occur with a probability given by a Boltzmann factor. And you would, so you can sort of make these models have some element of epistemic there, but really what you're interested in is whether the pure states themselves can be viewed as epistemic. So usually psi-epistemic is what we're explicitly considering, because you can add additional sorts of randomness. I don't know, did that make some sense? A little bit? So
Why are we only interested in pure state?
that's a good question, because I think a lot of the intrinsic randomness, I mean, the intrinsic randomness of quantum mechanics is sort of, so if I have some rho, I can always write it as this is a probability distribution. Maybe I'll write it as P to make it explicit. P times psi I, where these are pure states. Now, the fact of the matter is that this kind of randomness is not typically considered to be sort of like a fundamental quantum sort of uncertainty. This is exactly the kind of uncertainty you would expect from even just classical mechanics. You have some way of generating an ensemble, and you pick out these pure states with some probability. So the reason that you might consider pure states is because you still have these probabilities showing up. You can still write down the Born rule. And in some case, even though they're, it's this restricted case, oftentimes you can generate these contradictions just using the pure states. So really, like probing the pure states when you can and can't, because if you can't do it for pure states, you might still be able to satisfy this condition for mixed states. If you mix this enough, like just 1 over n, and you just make this thing be something like a completely mixed state, then you've sort of washed out all of the sort of quantum behavior. I will get rid of that real quick. Okay, so a couple of examples. Okay, this is like the most straightforward. I mean, this is essentially like the textbook definition of what this psi complete is. So this is a model going to, let's see if I get the spelling correct. Meti and Bugaiski. So this is their model, and it consists of 3 pieces. Lambda is the projective Hilbert space. You have that P lambda given P psi is a delta function. That should be a delta. And this is lambda psi. And then in order to sort of reproduce the Born rule, you need a rule for how to pick the indicator function. And here it is P of k given m comma lambda is given by the trace of the projector onto lambda ek, which is just lambda ek lambda. And it's not hard to see how this one reproduces the Born rule. I didn't write it down, but if you just sort of look at this expression, this guy is a delta function. And then this one, so this delta function will map this to a particular quantum state that we're interested in, and then you sum over all lambdas so that you will just get that this thing, you get precisely that psi, or maybe I should write it in the original way, trace. My preparation is psi so when I write this down, I have lambda delta lambda psi times lambda ek. Kills the delta function, centers this at at psi precisely, and then you just recover the left-hand side. It's almost just guaranteed to work by definition, but the idea is that you can actually just take standard quantum mechanics and fit it within this model by taking maybe just the most straightforward interpretation of it. Quantum states are the real things. A preparation is going to be given by this delta function. The indicator functions, these things that tell you what the measurement outcomes look like, given some lambda, is precisely just something of this form, which is already kind of assuming the Born rule. So maybe this is not so creative. So let's look at least one other model, which is one due to Cohen and Spekker. Okay.
Where did we get this integral from the last?
The integral, it was part of the definition. And also, so the projective Hilbert space is, this is a manifold. So we would do an integral over all possible quantum states. Essentially, you're thinking of like some unit sphere inside of the Hilbert space, and then you're quotienting out, basically identifying different states with the same overall phase. So it's a manifold called the projective Hilbert space, and so you have this integral here just on general terms, but it is in fact an integral because you have an infinite sort of continuum manifold of states. Okay, so this model is, so we're going to restrict to two-dimensional Hilbert space and take lambda is equal to pH. We take p of lambda given p psi equal to 1 over pi so this is the Heaviside function. Is there another name for this? The something Heaviside function? Anyway, yeah, so this guy is 1 for x greater than 0 and 0 otherwise. And also, these are vectors in R3. So psi lambda okay, and I guess there's a third piece. And the third piece is going to be P of, hopefully this notation will be okay. So these are, if you guys remember from the block sphere, there's a particular representation. So for qubits, you can think of any quantum state as being parameterized by a vector in R3. So basically, we're identifying these preparations precisely with the corresponding block vector. That's where the vectors are coming from. And so lambda is also some quantum state because we're taking lambda equal to the projective Hilbert space. So we can think of each of these as having their block vectors. And sort of one thing that I wanted to point out here is that even though lambda is equal to pH, much like this, no problem, we actually have that. Can anyone think of what kind of model this is? Is it, within our table, where would it fall? Well, it's not psi complete, right? Because we defined a preparation procedure that's not the same. So it's not psi complete. Is it psi? So therefore it's psi incomplete. Is it psi ontic or psi epistemic?
It's ontic, right?
Well, the test is precisely this one, right? So we take the preparation procedures, we multiply them for different psi, and will they be always zero for distinct quantum states? Because this thing is just going to give me the cosine of the angle between them, right? So in principle, I could have, for fixed lambda, I could have different quantum states that have the same cosine. So, right? So therefore, I actually will have that the product is not always zero. So this guy is going to be psi epistemic plus, because it's not complete, it's incomplete. So this will be in this one. So let's see. Psi epistemic plus psi incomplete. Okay.
Is there a difference between lambda is equal to the projected Hilbert space, or it's just isomorphic?
I think I probably meant to say isomorphic. Okay, so I think that we'll take a little 5-minute break. Is that okay? Okay, so a little bit of a shift in direction, because there's also some mathematical preliminaries I wanted to get to. Okay, so let's say that this is something of a primer on convexity. I've used that term a little bit already, so I will just sort of elaborate on a little bit of the mathematical background. I guess the references here, and I'll upload the text. The ones that I often use, but it's not limited to these. Well, for this particular part, I think I used chapter 0 of Ziegler's book. I should make this look like a 0 or something. And then chapter 1 of Matusik. Okay, so first, does anyone know what an affine subspace is? Raise a show of hands. Okay, so very nice. So we're gonna start with affine stuff before we get going. So suppose that we have a vector space. Typically, we'll be thinking of finite dimensional, and let L be a linear subspace. So L is a linear. Okay. So any affine subspace is going to be of the form X plus L, which is a subset of V again, where X is also in V. Okay, so what's the simplest example of an affine subspace that you might think of? Oh, I mean, even simpler. I mean, yes, RD is technically correct. It's a specific example of RD. What's an affine subspace in R2?
I mean, just any line.
Yes. Okay, very nice. So if I have just any line AX plus B, then okay, so we have the linear subspaces. I'll make this look a little colorful. Why not? We have our linear subspace, and then we have the translation of this. So this would be my L. This would be my A. Because in this case, I guess if I had this going through the origin, which I should have been, my B is right here. So essentially, we can just think of, we can just think of affine subspaces as these translations of linear subspaces. So in general, out of curiosity, what's another way to think of a linear subspace? I know there's going to be many answers. I'm driving at a particular one. I can think of linear subspaces. If I think more like a linear algebra type of setup, a linear subspace is.
Maybe a kernel of a linear function?
Yeah, exactly. So you have, for linear subspaces, you might have something like solutions to some mx equal to 0, some solution to a set of homogeneous equations, and the affine case would be where, I mean, this is a vector appropriately sized. So let's see, maybe I'll try and fit this in like this. This seems to be messing with me. At the risk of being too trivial, yeah, you know what? That's a little bit much. So, okay, from this perspective, what would you say if I have two affine subspaces and I take their intersection? So all the points that are in, so if I say, okay, A intersected with A prime, is there anything that in particular that I can say about this intersection? Sorry, it should be prime. Both affine subspaces.
I mean, I guess it becomes an affine subspace again, as long as that is the non-empty.
Yes, exactly. As long as, well, I guess even if technically it's still, I think it still works even if it's empty, right? What did I want to say about this? Yeah, and so there's a couple of different ways to look at this. For me, the easiest way to see that is that if I have a solution to a set of inhomogeneous linear equations, and when I take the intersection of them, essentially what I'm doing is doing something like, okay, now I'm going to look for solutions to m and m prime, x equals b, b prime. So again, since this is the definition of an affine subspace, this will also be an affine subspace. You're just stacking constraints. So here's an interesting, or a useful fact rather. So the dimension of an affine subspace, in fact, maybe this is more like a definition really, is equal to the dimension of the corresponding linear subspace. Does this seem to make sense? It's okay. Basically, I just translate this thing back by that vector, and then say what is the dimension of the linear space, and so it seems to hold water. Let X subset of V, then it's affine hull, denoted aff of E, smallest affine subspace. So, I mean, you could write this down a little bit more technically, but the idea is because we know that the intersection of affine spaces is again affine, you can just say, okay, I have some subset of my vector space, and then take all of the possible affine subspaces that contain X. So imagine that this was actually in 3 dimensions, and then you just start thinking of all of the different affine subsets. It could be all of R3, or sorry, yes, all of R3, and then say, okay, but there's something smaller. So then I go down to the plane. And so you can just keep looking using this intersection property. And so you can find a smallest, and by smallest here I mean a lowest dimension affine subspace containing X. So does anyone know what an affine combination is? Have you encountered this? Okay, so let's see, did I? Okay, so a linear combination, we're all comfortable with this. Basically, I have some basis for my linear subspace, and I can write any vector in that subspace using just arbitrary coefficients using that basis. So for an affine combination, we are going to instead consider the linear span of some set we want to consider the affine combinations of this set. Let me write it up here. Some vi, I equals 1 to D. And this is a subset of V. Sorry about that. So in order to sort of understand what an affine combination is, let's consider the linear span of the following related set, which is Vi minus, so the indexing should start here from 0, sorry. This is 0, Vi minus V0. And so for any x that's in this linear span, we can write it as follows. I equals 1 to D, alpha I, arbitrary real coefficients of Vi minus V0. And so just rearranging terms, I get that this is sum I equals 1 to D, alpha I Vi minus, or I will keep this as plus, the sum I equals 1 to D of alpha I, maybe a minus in here, Okay, so I have this piece. So if I write x plus some V0, then this is going to be equal to did I make some assumption about this? 1 second. I think I'm assuming that this is linearly independent. I think I should have defined linear independence and affine independence first. Oh, that's not good. Okay. Well, let's assume, and we'll return to this point, that this is linearly independent, this set. So we have a set, this set will be later considered what's called affinely independent. And affine independence just means that if I subtract by any element here, then the remaining set is linearly independent. Because essentially what you're doing is you're taking out one of these, one of this x, and then you're basically looking at x inside this, or I'm mixing up letters now, but you're looking at some element in here, looking at its linear combinations, and then translating back. So when you do that, x plus V0 is going to look something like I equals 1 to D, alpha I Vi, plus, when I add V0 here, I will have 1 minus I equals 1 to D, alpha I V0. So what this means is that, and this thing, okay, so what this is looking like is a linear combination of elements in here constrained to the following, that sum I equals 0. So if I consider this alpha 0, sum of alpha I equals 1 minus sum I equals 1 to D of alpha I plus sum I equals 1 to D alpha I. So affine combinations are going to be linear combinations constrained to a certain, with the following constraint, that the sum of the coefficients equals to 1. I want to give an example. Affine. So maybe I should say this first before we go to the example. So then, this thing that I called the affine hull before, you can show that this is precisely, so if I have the affine hull of a set of points, I equals 0 to D, then this is precisely the set of all affine combinations, I equals 0 to D, alpha I, Vi, such that sum I equals 0 to D, alpha I equals 1. So the convex hull, which is the smallest affine subspace that contains X, so if this is my X in this case, then the affine hull is precisely the set of all affine combinations. And we have that and we have also, let's just get these on the board, that Vi I equals 0 to D is affinely independent if and only if Vi minus Vk is linearly independent, equals I not equal to k, say, is linearly independent, and then for every k equals 0 to D. So what's the example going to look like? So if I have the following set of points, V1 is equal to 0, 1, V2 equals to 1, 0, then what is the affine subspace? As you might guess, it's going to be this line going through here. What's the way to see this using these affine combinations? In particular, this definition. It's going to be the following. Consider any alpha V1 plus 1 minus alpha V2. Then this will be equal to alpha 1, 0 plus 1 minus alpha 0, 1, so that this is alpha 0 plus 0, 1 minus alpha, maybe put some commas there. And this is some point z, or maybe p rather. And p has coordinates px, py. And so all I want to show here is that this definition reproduces the definition of a line that we previously had. That's what I'm trying to do. So we have this definition, all possible affine combinations is going to give me the affine hull of a set of points. Here's my set of points. We know geometrically that this is the affine subspace. Now, where does this come from? You can sort of see that what's going to happen here is now that Px is equal to, just by comparing this, because this is alpha 1 minus alpha, so Px is equal to alpha, Py is equal to 1 minus alpha, which is equal to 1 minus x, which is precisely what we have here. So the definitions overlap in the way that you would hope for. Unassigned piece of homework, or maybe I will make it part of the homework. We'll see. Do this for V3, just add another 0 here and see what that one looks like. Sorry, we end at 45? Okay. So, which one of you knows what the definition of a hyperplane is? Okay, I will write it down so we don't have to. So I will call this thing H, and it's a subset of RD, just to be explicit for the time being. And the hyperplane are solutions I equals 1 to D. This is linear. Alpha I xi equals 0 for a normal hyperplane. An affine hyperplane, can anyone guess how to modify this to get an affine hyperplane?
Well, you just like move the whole set of points along. So
Yeah, so affine hyperplane is the same thing, but we have solutions to for some b. Now, okay, here's a fun one. So suppose that, maybe we write this as a lemma, if y prime in H implies that lambda y plus 1 minus lambda y prime in H. I think that the details are, I mean, I can do them, they will be in the notes, and maybe I want to save some of these manipulations for the exercise course, but if you were going to take a crack at it, it's not so bad, right? If I know that y is in H, then what that means is I know that it satisfies this for the components of y, and also y prime also satisfies this. And then the fact that this is a affine combination, I will have a bunch of terms that have to do with the coefficients, but because this is affine, it will equal 1, and then the right-hand side will also be, we already know that the other statement is true for linear, so if I have a y in the linear hyperplane and another y, then of course any linear combination will also be in the linear subspace. And then the affine combination constraint of summing the coefficients to 1 will guarantee in the affine case that I get the b here. So a half space. Has anyone encountered one of these? Okay, so I will denote this H plus, and this thing will be such that, I guess I used alphas here, but I should have used C's. I'll use the same notation. Alpha I xi greater than or equal to b. So this is the positive half space, or non-negative half space rather. You can also define the same thing with the inequality going the other direction. And then, so any half space partitions the space into 3 parts. You could have the part that's actually on H. You could have the parts that are strictly positive, strictly negative. But you usually want these to be closed, so it's better to split it into H, H minus, and H plus so that they include their boundary. And so these are going to end up becoming important because when you talk about Bell inequalities, so just to sort of connect to this sort of more foundations perspective, I mean, what is a Bell inequality? It is literally just a half half space inequality of this type. And usually in foundations, you're given either, oftentimes you're given a finite set of points, these V's. And then if you ask for what are the, and I say, okay, now take what's called the convex hull. We'll get to convex hull. I take the convex hull of these things. So I give some finite set of points, and then I fill them in. This is going to be the convex hull. The convex hull is just the affine hull where the coefficients are restricted further to be non-negative. So instead of this line being all the way here, you just fill in this line only to include the non-negative coefficients. That will be the convex hull. And then you ask the question, okay, what are the half spaces that delineate this one from this one? And so any polytope or any convex set that's the convex hull of a finite point set can also be written as a set of the intersection of finitely many half spaces intersected. So we will sort of be building towards that. In the recitation section or the exercise section, I want to take just 15 minutes of your guys' time to talk about some of these convex notions and sort of tidy that up. And then we will discuss some of the related problems to what will be on the problem set, if that's okay with you. Okay, I think that that's good for now because the next section I have is about the convex part, which I want to do it fresh with more time.